This is the fourth part of the module of the engineering science course for the second part of the semester. The module covers energy analysis of closed systems, involves moving boundary work, energy balance for systems of pure substance, specific heats, and energy balance for ideal gases. This is the first part of this module. Previously, you have learned that energy can be transferred to or from a system in these forms. 1. Via heat, 2. Via work, and 3. Mass flow. For a closed system, the only way the energy of the system, E, can change is through heat or work interaction, or both. Right? So imagine you have a system, a closed system, which is initially at state 1, or initial system subscript I. It has an energy E. It has properties like specific volume, pressure, etc. and others. And then the system undergoes a heat and work interaction, any one or both. And at the end of that interactions, the system now has energy 2, final energy, and properties that you know. So now the change of energy of that system is just the final energy minus the initial energy. I prefer to use F and I to make it more general. You can use 2 and 1 respectively. So the change of energy is due to the heat and work interaction. We'll explain the negative sign later, which is equal to the change in kinetic energy, the change in potential energy, and the change in internal energy. Now, if your closed system is stationary, which is most often they are, then your delta KE and delta PE are 0. So the change of energy is just equal to the change in internal energy, kilojoule. For heat, it is quite direct because you will not go into the different mechanisms of heat transfer. It's just heat going in and heat going out. But work, there are many types of work involved in this analysis. It is usually defined as a force acting through a displacement x, like a piston moving over distance delta x. So it's the integral of that force acting over the distance dx, such as given as for 1, it's PdV. W can be also work to raise a weight, stretch a wire, move charged particle through a magnetic field. A form of mechanical work often encountered in a closed system is a compression and expansion work of a gas vapor associated with the piston cylinder arrangement. Now, the expansion and compression work done in a quasi-static process is called moving boundary work, or just boundary work, or PDV work. You remember in the first module, what is quasi-static process? It's when the change during the process, the change in properties of the system during the process is negligible. So the boundary work is the work output. Now, P is the absolute pressure, always positive. Now, it is the dV that is positive for an expansion work because the final volume is greater than the initial volume, and negative for a compression work. Let's see why. How? For the total boundary work, WB, from state 1 to state 2, it is given by 4,2. It is represented by this continuous line. An example for expansion, you notice that the final volume is larger than the initial volume, and the pressure has dropped. It's an expansion process. So our area under the curve is actually the boundary work. See, note that the process path is continuous, indication of quasi-equilibrium states pass through from state 1 to state 2. So these are stages of quasi-equilibrium states. Let's say from 1 to 1A, 1A to 1B, to 1C, etc. Up to state 2. So a series of quasi-equilibrium state pass through. So in this case, the changes from 1 to 1A, 1A to 1B, and so on are negligible. But in the end, you have this final state of state 2. The boundary work is positive going from left to right and negative from right to left. This also means if we try compressing the gas, let's say from state 2 to state 1, you can label it 1 instead, and this is 2. Following the same pattern as before, we could follow the same path, no history. A reversible process. Is that possible? No, of course. Like if I have a cup of coffee, a hot coffee, and it has cooled down, if I want to warm it up again, I would have to put it in a microwave to heat it up again. Now, is that no history? No, of course not, because I need electricity to run my microwave. So changes have been made to the surrounding, although my coffee may have gone back to the initial temperature. So a reversible process is impossible. Now, can we use WB integral if the line isn't continuous? That means it's a broken line, as indicated here. As in the case of a fast expansion, you withdrew you have withdrawn the piston suddenly. So would area under the curve 1 to 2 still represent the integral? You remember in your first year math class. Of course not. Yes. A system in an initial state which undergoes the process to a final state then returns to its initial state without affecting the system and its surrounding is said to experience a reversible process. You've been introduced to this in the first module. This is an ideal process actually, which doesn't really exist. But most processes may be assumed to be reversible if the degree of irreversibility is low. For instance, like the quasi-static compression and expansion of gas in a cylinder. So we may assume because the changes in stages are small and may be ignored. Work depends on the path. Say we raise the temperature of a fluid in a tank via external heating, resistant wire, and paddle wheel. Each amount of work required is different even if the final state is the same. As shown here, you see we're going from the system state 1 to the final state 2, different path would have given the same change in the properties of the system. In this case, we use the volume or the pressure. So, because work is a path function, remember the point function? Properties of the system are point functions. So, we have this boundary work represented by the integral of PV. It may be solved if, for case 1, PV is a constant, say some pressure. In this case, you can take out the constant and solve the integral. Case 2, there is no change in volume, such as in an isochoric process. Then dV is equal to 0, so boundary work is 0. It's not moving because the volume is not changing. Third case, isothermal process for a gas. That means you have PV is equal to MRT. You can rearrange and get it in this form. Now for case 1 and 2, they are applicable to any kind of fluid. For case 3, only for gas, ideal gas, because you have used ideal gas equation of state here. 4, if you know the PV relationship, so you may solve this integral. Let's look at case 1 first. Isobaric expansion, compression, because we said P is a constant. So the initial pressure is equal to the final pressure. So I've used 1 to indicate the initial state and 2 the final state. Then for a constant mass in a closed system, controlled mass, we have the boundary work given here. You can take out the pressure because it's a constant, and you may solve the integral to get 4/6. If your boundary work turns out to be negative, such as in the compression, work is being done on the system. If WB turns out to be positive, such as in an expansion, work is being done by the system. Case 2, isochoric heating or cooling process. Now, the change in volume is equal to 0. Of course, the boundary work is equal to 0. No boundary work. Simple, the simplest actually. Case 3, we have isothermal expansion or compression process for an ideal gas. This is only applicable for ideal gas. Now, case 1, case 2, they are applicable for any kind of fluid, vapor, gas, etc. Now, for case 3, you utilize the ideal gas equation of state, which means that P1 V1 is equal to P2 V2, which is equal to MRT1, which is equal to MRT1, T2 actually here, yes, which is equal to a constant. Yeah. Now, if you solve that, you substitute C over V, you may solve that, you can get a logarithm, and you have actually 8 forms of the solution for the boundary work. Yeah. But these 8 forms are only for ideal gas. For any other working fluid, you may have to solve it if you know the relationship between P and V. Yeah. So depending on which parameters are known, P1, V1, T1, P2, V2, T2, you may determine the unknowns. You have to select which one of the 8 forms is most appropriate to determine your unknown parameter. Yeah. The mass is a constant in this case. Finally, in case 4, a polytropic expansion compression process. So we have here, as been introduced in the first module, PV to the power of index n, which is a constant. In this case, it means P1, V1 to the power of n. The n is only applicable to the volume, yeah? Which is equal to P2, V2 to the power of n is a constant. So you may substitute that into your boundary work integral and solve it, and you get 4,9. Yes. So for an ideal gas, 4,9 can be rewritten in the form of 410, provided n is not equal to 1. Since for ideal gas, PV is equal to MRT. So you can have this 410 version. Now for the special case in the polytropic process, as n is equal to 1, PV is n is 1, so it's just PV. This is the isothermal process shown earlier in case